Hello and welcome back to Real Analysis. And first, many thanks to all the nice people that support this channel on Steady or PayPal. Now today in part 41 we will finally talk about the famous mean value theorem. Indeed, this theorem we can immediately visualize in a nice way. Now I can already tell you, the mean value theorem applies to all functions that are defined on a compact interval and differentiable. Therefore, let's call the interval on the x-axis simply AB. Okay, and now we look at the mean slope of the function, which is the slope of this secant. And of course, we can immediately calculate this by f of b minus f of a divided by b minus a. Now the claim of the mean value theorem is that we also find a tangent with the same slope. So in the picture this would mean we can push this secant until we find the correct slope. And the corresponding point in the interval AB we call x hat. All in all, this is already the whole mean value theorem. In other words, at this point we are ready to formulate it. The only assumption we need here is a differentiable function f. F should be defined on a compact interval, so we choose it as AB. And of course the whole thing only makes sense if a is strictly less than b. Then the claim is there exists a point x hat in the open interval. So indeed we find an inner point. And for this point we have the property that f prime of x hat is exactly the mean slope. So you see, the whole theorem is very easy to formulate and therefore also to remember. You can simply say the secant slope is given by some tangent slope in the middle. However, please note here, the statement of the theorem is the existence, not the uniqueness. So it's definitely possible that you could have many x hats with this property. For example, for a constant function f, you immediately see this. Okay, then let's use the next minutes to prove the mean value theorem. And of course, we will need Rolle's theorem from the last video. Indeed, we can immediately apply it in the case that f of a is equal to f of b. Because in this case, Rolle's theorem tells us there is an x hat in the open interval AB such that the derivative at this point is exactly 0. However, 0 is in this case the mean slope. Hence in this case we have already proven the mean value theorem. Therefore, the idea for the proof would be to reformulate the general case such that we can use this special case here. Indeed, this is not hard at all when we have the picture in mind. So in dark blue we have the function f and light blue gives us the secant. And now we want to push this value here to the same level as this value. Therefore, in the picture, this point should go down exactly by the amount given by the secant. So you see, the overall idea is simply to subtract the secant from the function. Then the result is that both points lie at 0. And we have a new function we can call g. Now the important thing here is that the new function g is still differentiable because it's a difference of two differentiable functions. And moreover, it's still defined on the interval AB. Now the definition we described in the picture is here given in this formula, which is exactly what we wanted, the function f minus the secant. So here we have the constant slope times x minus a point a plus f at this point a. And of course here a is the left bound of the interval. Okay, here because g is still differentiable, we can calculate the derivative. Of course you can apply the sum rule, so we have f prime minus the slope of the secant. So here you see, we are already very close to the mean value theorem. Now the only thing that is left to do here is to apply Rolle's theorem. Please recall, before we could use it in the case that the left value is equal to the right value and then we found a middle point such that the derivative is 0 there. However, now we are in the case that f of a is not equal to f of b. But we shifted the whole problem such that g fulfills what we want. If you don't believe it, put a and b into the definition and you see it. Hence now we can apply Rolle's theorem and find a point x hat where the derivative is 0. However, vanishing the derivative for g means that this expression is equal to 0. So we simply bring f prime to the other side. So not so surprising, we found our mean value theorem. And indeed, this is the whole proof. Okay, then for the end of the video, let's look at an application of this nice theorem. Again, let's take a function f defined on a compact interval. And of course, it should be differentiable. Now assume that we know that the derivative is positive no matter which point x we put in. Then we can look at two arbitrarily chosen points x1 and x2, where x2 is greater than x1. Then we can apply the mean value theorem, where we shrink the domain to the interval x1, x2. This means that we find our point x hat in the open interval x1, x2. And as before, at this point we find the mean slope. Then we can just multiply x2 minus x1 on both sides and get this equality. Now we can put in our two assumptions. First, we know the derivative is positive. And secondly, we know x2 minus x1 is positive as well. Hence, we can conclude the left-hand side of the equality is also positive. Which means the value fx2 is greater than the value fx1. And since the numbers x1, x2 were arbitrarily chosen, we conclude that the function f is increasing. Or more concretely, we would say f is strictly monotonically increasing. Now indeed, this is a nice result we immediately get out of the mean value theorem. So in short, we can simply say, if the derivative is always positive, we get out a function that is at all points increasing strictly monotonically. And of course, with a similar proof, we can also look at cases with a negative derivative. This case might not surprise you, we simply get out that the function is strictly monotonically decreasing then. In addition, we can also look at the cases where we don't have the strict inequality. This means if you look at the proof, we will also lose the strict inequality here. Otherwise, the proof works exactly the same. However, since we lose the strict inequality, we just have functions that are monotonically increasing or decreasing. Okay, with this we now have a common application for derivatives when we want to analyze functions. And of course, this will come in handy a lot later. Therefore, I really hope I see you in later videos. Have a nice day and bye.